So, hello, this is Chapter 5, Volcanoes and Volcanic Hazards. The most well-known volcano to most Americans would, of course, be Mount St. Helens. And Mount St. Helens, of course, blew up in 1980 and was a very famous destructive event, right? Uh, if you look at these pictures, this is a before and after of the eruption of Mount St. Helens. Noteworthy here, I'm going to point out two things. One is the amount of mountain that was actually blown off. You can see the sketch, the dotted line sketch here of the size Mount St. Helens was. 1,350 feet of the mountain erupted and was exploded and became particulate and flying debris after this eruption. Second thing I want to point out, and it's shown here at that Spirit Lake, everything around this mountain was completely destroyed. Before the eruption, nice lake, woodlands, animals, hikers, things of that nature. After the destruction, nothing. The lake, Spirit Lake, completely filled in with rubble and what have you. So a massive, massive event Mount St. Helens was. Here's a couple pictures of the actual explosion. And again, you can see the height of the mountain in A, and it just comes crumbling down. Massive destruction happening here. And it really goes to show the amount of power that happens in a volcanic eruption, right? This is a solid chunk of rock, this mountain. But there's so much energy in a volcanic eruption, it literally tears 1,350 feet of solid rock off the top of a mountain and shoots it into the air, right? Look at C and D. That's rock flying through the air. Many, many tons of rock flying through the air. Another picture of it, just the ridiculous amount of energy on display here, right? Just ridiculous. And Mount St. Helens, large volcanic eruption, not the largest, right? There are bigger ones throughout recorded history that have done even more so damage. We're just lucky that Mount St. Helens was in the middle of a park as opposed to right next to a large populated town, for example. But yeah, devastation is really the only word you can use to describe an event like this. The ash covered thousands of square miles. The explosion, we saw the clouds and felt the explosion, not physically felt the shaking, but we had the aftermath of the explosion felt throughout the United States. This affected the weather in North America. That's how big this explosion was. Again, when you're talking about a volcano erupting, especially explosively, we'll get to that, it's a big event. These things can affect the world's climate, in fact. Of course, the devastation, massive trees literally being knocked over by the concussive force of the explosion, being shattered, as shown in this way, leveled, right? It's a volcano. It's not a joke. It's massive, right? So, quick, cool little intro to volcanoes. Let's get into some facts and some information now. Nature of volcanic eruptions. When a volcano erupts, it erupts in more or less two different manners. It erupts, by manners, I mean viscosities, or how plasticky the flow is, how watery the flow is. A volcano can have a very, very viscous or a low viscous eruption. Viscosity, of course, being the material's resistance to flow. A lot of viscosity is similar to molasses or syrup. Low viscosity is water, gasoline, something like that. Why do some volcanoes erupt? Why do some volcano eruptions have very high viscosity and very low viscosity? Well, that ties back into the last chapter with magma and lava. The temperature at which the volcano erupts, because not all volcanic eruptions are similar. Not all volcanic eruptions are comparable to each other. The volcano sits upon magma, sits upon lava, and as we discussed last chapter and the chapters before that, different parts of the world have different chemical compositions, different heats, different temperatures, different pressures. This all plays a part into a volcano, how it erupts, why it erupts, and what happens because of its eruption. last chapter, we talked about the temperature of the magma going on here, the composition, the gases involved in it. All these can play a factor into what happens with a volcano. These factors determine the violence or explosiveness of volcanic eruptions. These three factors control the viscosity of the magma, which in turn plays a part in, again, that violence, that explosiveness. What is erupting? How thick is it? How much energy does it need to travel? How much energy can it give out? Things of that nature, right? This ties in very well to the last chapter, which is why it follows it. Temperature. How does temperature work? The higher the temperature of the magma means the melt has a decreased viscosity. A decreased viscosity, a high temperature melt, is less explosive. Contrast that with a low temperature melt, increases the viscosity, makes it more syrupy, and gives it to be more explosive. Well, why do you think that is? This is a result of how much energy does it take to actually move the magma, move the particulate, right? If you slap a puddle of water, the water flies up to the air, right? It doesn't take a lot of energy to do that. How much energy you need to put into your hand to slap a puddle of syrup and have it go flying? A lot more energy. So it takes a lot more, a lower viscosity takes less energy to be explosive. I hope that kind of makes sense. The syrup analogy is the best I can do, really, right? If you don't like slapping syrup, pouring syrup out of a bottle, it takes a lot more energy to squeeze syrup out of a bottle than it does to squeeze water out of a bottle, right? Chemical composition, as we talked last chapter, plays a big role in determining viscosity. Lower silica, lower SiO2 content results in lower viscosity and a more fluid-like behavior. And lastly, the dissolved gases, the volatiles, as we discussed last chapter, can affect the magma viscosity, therefore affecting the magma's explosiveness. The gases affect the mobility. The gases expand as magma nears Earth's surfaces, resulting in a decrease in pressure, and this plays directly into the viscosity, which plays directly into the violence or the explosiveness of the volcano. So, to summarize, fluid basaltic lavas, we talked about those before, generally produce quiet eruptions. Hawaii is essentially constantly erupting. Hawaii is constantly letting out magmas and lavas, but they're not murdering people because these have very weak eruptions. They're not causing the same amount of damage as a high viscosity lava, a rhyolite or andesite lava, such as Mount St. Helens. Right? Sure, that's dangerous, but that's going 30, 50 feet in the air, not, 2,000 or 3,000 feet in the air. This lava is drizzling down around it, hitting, a half an acre of total land, not the entire continental United States. That being said, I wouldn't want to be next to that volcano either. It is still magma, right? Big distinction, big difference between these two pictures. This guy probably could feel the heat of the volcano. This person had to have a telescopic lens, right? But they are doing technically the same thing. It's just what's exploding that's different. Cool. So volcanoes, of course, are known for the plumes, the eruptions, and we'll get to that. But more practical side of things, when you think of lava, you think of a lava flow, right? They can be many different types of lava flows in here. The two types we're going to talk about coming from the Hawaiian names of these are Pahoehoe and lava flows. I'm pretty sure I pronounced that correctly. Forgive me if I'm wrong, especially on the second one. But a Pahoehoe and lava flow are two different methods that the lava can move, again, depending on the characteristics of the lava. The Aha and Pahoehoe are both shown in this picture right here. The is a rough, jagged, blocky lava flow, and it sort of looks like, I guess, if brownies could be dangerous, like crumble up a brownie and push a brownie towards you, that's a approach to aha, cement flowing towards you slowly. Pahoehoe, as shown here, gives this cool ropey, smooth texture to it. These are both lava flows, but depending on the way the lava came out and what the lava ran into, can produce these two different effects. If you want, you can go watch a video on YouTube of each of these in action. They're pretty cool looking, right? Here you have the lava slowly pouring out over the top of rock, not a lot of soil for it to mix up with. So it's flowing, roping out, very viscous liquid we have here, producing these wrinkly texture, right? The lava is kind of going to do what it wants. It's going to make its own caverns. As we talked about before, lava produces igneous rock. We see igneous rock everywhere. This is a ridiculous picture. That guy is, wow, that's an amazing shot, right? He's standing on top of a lava tube, a big amount of magma popping up out of the world, and everything he's walking on is cooled magma, is cooled lava. That's igneous rock he's currently walking on. You can see that pahoehoe texture down here in the bottom left, right? That's because that lava is very, very recent. However, pahoehoe and textures refer mostly to surface lavas. What if you have a volcanic eruption underneath the water? Usually you get what we term as pillow lava. Pillow lava is what happens when the lava has to cool very quickly, right? Lava expands out and essentially 360 degrees from the place to where it's leaving, and it's all cooling very, very rapidly because it's in water. So it forms these pillowy textures, forms these toothpaste-looking shapes on the bottom of the ocean. You can watch videos again. I have a click here if we were doing this in class of this stuff happening actively in the bottom of the Atlantic Ocean. Very cool stuff. Again, I suggest you Google pillow of the lava and watch it form for a little bit. It's oddly relaxing. So, as I talked about before a bit, go back into this real quick, the dissolved gases in the lava can play a factor in how they form and which of these two they become. These dissolved gases are the volatiles, called volatiles because they are volatile, right? They can have some explosions. The vast majority of your dissolved gases are going to be essentially water vapor and carbon gases in the atmosphere, because the atmosphere is what gave those gases in the first place. Not always. You can get nitrogen, sulfurs, things of that nature, but 9 times out of 10, you're going to have boiling water vapor, essentially. You had some water stuck in the magma. It boiled out, but it didn't have a chance to leave because it's, again, stuck in the magma. It's like a bubble. Cool. That was lava. That was the melted rock that we talked about in the different ways it can form. Let's talk about essentially the not igneous rock. Well, it's still igneous rock, but this is the non-magma stuff. Pyroclastic materials. Essentially, these are all the chunks of rock that blow up when the volcano erupts. Those big pillows, those big smokestacks coming off of Mount St. Helens, that's flying rock material, pyroclastic material coming out of the volcano. And this pyroclastic material depends a lot on, again, where the volcano is erupting, how the volcano is erupting, and what the volcano is made out of. It can vary greatly from a volcanic ash, which is essentially an ash, right, to small cinders, small chunks of rock flying, to big chunks of rock flying. You can get things the size of small vehicles being shot into the air, and well, you don't want to be below them when they land, right? These are called bombs usually, or blocks technically, but usually refer to them as bombs. And that's, right, very large. You get hit by a volcanic bomb, you're not happy about it. Picture volcanic ash. You know what ash looks like. Volcanic ash is ash from a volcano. zoom in on the cinders and the lapilli, I'm going to assume. Again, my pronunciation of these is not 100%. Zoom in on the bottom. Cool. Scoria and pumice would be two examples of pyroclastic materials. These are the ash and the cinders and all the stuff that comes off the volcano. If it gets the chance to form together, build together, and harden, you can get scoria and pumice. Likewise, just the explosive nature and the energy of this pyroclastic material can shoot these things out as well, right? Scoria is a vesicular rock, commonly having a basalt acidic composition, whereas pumice is your low density, super low density andesitic to rhyolitic composition. Scoria and pumice are sort of the same formation, just what's the silica content of your rock? Are we talking basaltic all the way up to rhyolitic, right? Cool. So we talked a bit about volcanoes. We talked a bit about what comes out of volcanoes. Now let's go into the general features and the structure of a volcano. General features include a crater, a caldera, cones, magma chambers, conduits, etc. We're going to define crater, a volcano crater, as a depression at the summit that is less than 1 kilometer in diameter. A caldera would be greater than a kilometer in diameter, and essentially they're describing the same thing, just one smaller, one's larger, right? This graphic here is a cartoon showing all the different parts of a volcano and what's going on. We talked about magma chambers back in the last chapter of the igneous rock. The magma chamber is where the rock is melted, where it's under all this pressure. The conduit arrives where you have the rock finds a crack, the magma finds a crack in the bedrock, overlaying bedrock, and starts pushing through, breaking the rock apart, right? Eventually, that conduit's going to find some place to break the surface and explode, and we call that explosion point the vent. Makes sense, right? A vent, it's a vent. You know what a vent is. When that volcano explodes, vents out, you get your pyroclastic material and bomb bursting through because this conduit is going through solid rock, pressuring through solid rock, and you also let out your lavas at this point. Again, once a magma breaches the surface, we call it a lava. Not the vast majority of the time, the conduit and the vent is not the only place where the lava and the pyroclastic material leaves. Again, if we go back to those pictures of Mount St. Helens, the entire side of Mount St. Helens blew off, not just a little hole at the top, right? Volcanoes will go wherever they can, the magma will go wherever it can find a path to take. So this is the basic understanding of a volcano. However, not all volcanoes look this way. This is a particular type of volcano, and hopefully by the end of me discussing the volcano types, you know what I mean. First of all, the first type of volcano is called a shield volcano. It's called a shield volcano because it kind of looks like a shield. It's very broad, it's slightly domed, usually basaltic in origin, and very large. They're produced via mild eruptions, such as the ones in Hawaii. What essentially goes on here is, as I said before, the eruptions in Hawaii are very low energy. The magma is not super thick. It can just kind of flow out slowly. The magma chamber is not under a stupid amount of pressure. And what happens is, as this magma chamber flows, the lava dries and the magma continues flowing, and it builds up on top of itself. The Mauna Loa, my Hawaiian's not the best, shield volcano has this large caldera, a 5 kilometer wide caldera that keeps just pumping out and slowly building and building and building this shield. Again, it's called a shield because it's gigantic and it kind of looks like a shield, right? This seems big and deadly and explosive, but it's not so much taller than those trees, right? We're not talking about a volcanic eruption that's going to affect much beyond its initial surroundings. And when this lava hits the air, it cools, it solidifies, and the next time lava comes up, it builds up on top of it, creating this large shield. Right? Again, looks dangerous only if you fall in it. This is the kind of lava that people go and visit when they visit Hawaii. This is an flow, right? It's not ropey looking. It essentially looks like a big scary brownie coming at you. And these guys are able just to turn around and walk away from it because the pace at which this flow is moving is such that you can outrun it if you want. The next type of volcano to discuss is a cinder cone. These are built from the ejected lava fragments, have very steep slopes, and are genuinely very small and sometimes occur in groups. Cinder cones happen when you have the lava shoot up out, but it's not a very large explosion, or it doesn't have a lot of pressure behind the magma. Cinder cones tend to form also on composite and shield volcanoes, which we'll talk about in a bit. But essentially, you could consider a cinder cone volcano to be the smallest of the volcanoes, the little baby volcanoes, if you want. They can still be dangerous, they can still be deadly, but these are going to affect an area larger than a shield, but smaller than Mount St. Helens, for example. Here's a pretty cool looking cinder cone volcano. And again, what is the volcano itself? The volcano itself is the lava and the pyroclastic debris from the eruption that built itself into this volcano. And you can see here, right, the lava flowed in a certain direction because the cinder cone broke on a certain side. All the lava flowed in that one direction. You still have the greenery and the grass all around it. Of course, these flows can still be very dangerous, very deadly. This happens to be a town, I'm not going to try to pronounce that was near a volcano. The lava flow overflowed it and buried this church, right? I say cinder cones are small, but they're still deadly to the surroundings. More deadly than a shield because shields kind of slowly erupt for thousands and thousands of years. This volcano erupts not for a shorter amount of time, but still does some erupting. That being said, the big volcano you need to worry about is the composite or stratovolcano. Mount St. Helens was a stratovolcano. This is the volcano you think of when you think of a volcano. 1,000 feet high, 7 miles wide at the base, interbedded flows of layer and pyroclastic debris. When you picture a volcano, you are picturing a composite volcano. This was an example of a composite volcano. Your mountain that explodes, lots of pressure, lots of damage, right? The way you would classify these is they're bigger than a cinder cone, but not as big as a shield. They are the deadliest, they're the most explosive, but they also last the shortest amount of time, right? The shield volcano we covered in Hawaii had been going for thousands of years. The cinder cone here, where's the picture, erupted for a while again. Mount St. Helens blew very quickly, right? Here's a good image of the size differentials we're talking about here. The cinder cone volcano is very small, not a lot of lava, not a big impact on its surroundings, but still an impact. The crater, the stratovolcano, the composite volcano, such as Mount Rainier, shown here, Mount St. Helens, larger than a crater, tend to be very destructive. Again, it depends on what the volcano wants to do at the moment. And the caldera at the top, absolutely gigantomassive, but slow erupting. You kind of need to walk into the volcano to have it damage you. Then again, if that shield volcano decides to be more eruptive someday, you have a different conversation, right? Volcanoes are going to kind of do what they want to do. Just because a stratovolcano, just because a composite volcano is near you does not mean Mount St. Helens is happening again. And you're not necessarily safe next to a caldera. right? This is kind of going over what I just discussed. We talked a bit about pyroclastic flows. That's the debris that flies out of the volcano. The hot gas moves very fast. Again, because you have the volcano erupting, such pressure, it can throw rocks the size of cars, miles and miles and miles. You got a lot going on here. And again, I mean, I don't think I need to explain what a volcano is doing to you. You've seen volcanoes in media countless times. You know what they're talking, I'm talking about here, right? Um, Big amounts of energy, shooting lots of rock and dust, very hot rock, very hot dust, very fast. I hope that Jeep gets out of the way. I don't know if it did. Here's an example of a pyroclastic flow from a volcano that destroyed a town. This town was not actually hit by the lava, right? This town was hit by the pyroclastic flow that travels much faster and still causes lots of damage because it's burning hot rock flying at, let's say here, 200 kilometers an hour, right? Super, super fast, super deadly. Do you really want to be hit by rock flying at 200 kilometers an hour? No, you don't. Neither of these buildings. But that's the result of this. That's what happens. Right? As I said before, with Mount St. Helens, the pyroclastic flow affected the weather and places out, Montana, the Dakotas, even to Wisconsin, Minnesota. They got some of the fallout from the pyroclastic flow from Mount St. Helens. Some of the dust from Mount St. Helens got high enough in the atmosphere, it was picked up by wind currents, and was deposited in Minnesota, Wisconsin. That's impressive, right? Pompeii, you're all familiar with that. Mount Vesuvius destroyed a town when it erupted in 79 AD. And as you can see, I mean, look at this image of Vesuvius. That's not what the mountain originally looked like, right? That looks a lot like, as it says here, the rim of a caldera. This mountain was once mountain-shaped, but the top of it exploded, blew off, giving you this unique shape that it has now. This big crack here, you can kind of connect the dots and see what Vesuvius looked like before it exploded. And when it exploded, the city of Pompeii was so nearby that the pyroclastic flow essentially coated and solidified the entire city and the people inside it, preserving them in rock. And there's pictures of people like holding each other and children being just destroyed, essentially. I mean, Pompeii is a very famous event in human history. Yeah, I guess I can keep talking about this, but volcanoes blow stuff up, right? Volcanoes are dangerous, volcanoes are deadly. Here you have the eruption cloud catching in the wind, and the wind taking, again, Mount St. Helens ash all throughout the United States. So lots of stuff can happen, lots of stuff can be dangerous. And there's further results of volcanic eruptions we'll get into later chapters, such as shown here: mud flows, lahars, domes collapsing, acid rain, ashfall, stuff like that. Right? We'll get more into lahars and mud flows as we go, but right, I'm repeating myself here on purpose. You have all this energy moving this very dense, very heavy material around. It's going to go, it wants to go. You have the collapse, let's say, from the side of the mountain. You get this mud, the slurry, the sediment flowing. Not a lot of stuff's going to stop it. All these busted up trees just flowing along, crashing through whatever it wants. And again, you can look at the size comparison of that person to this lahar. Go ahead, Google lahar if you want. You can watch these things happen. So, results of volcanic eruptions. When a volcano erupts, sometimes it keeps its form more or less. Mount St. Helens is still a mountain, right? But usually the eruption causes a collapse, because what is a volcanic eruption? That is the release of pressure. That magma chamber had a lot of pressure pushing up. When it erupts, After it gets done erupting, the pressure no longer exists, and the rock collapses down on top of it. This in this cartoon shown here, magma chamber erupts. The magma chamber is now emptied, more so than it was before. The rock collapses in to where the pressure once was held, and you get yourself a caldera, a depression in the land. That depression, for example, here can be filled up with rain and groundwater. You can get what's known as a caldera lake. I believe the Lake of the Clouds, if you live in the UP, is an example of one of these, I believe. It is an example, right? Crater Lake in Oregon, nice little Wizard Island. This picture, if you go back before the volcano erupted, would have been an entire mountain. You can connect both sides of this caldera lake, bring it up to a point that's the size of the mountain. Notice that stuff isn't there anymore, right? Because when this mountain exploded, when this volcano erupted, it shot all the rock that would have taken up Crater Lake. It shot all that rock up into the air and into the surrounding environment. That's huge. That's big. Pyroclastic flows. We've talked a bit about pyroclastic flows. I'm not going to get too much into this, but what this slide is pointing out to you is that volcanoes are common. Volcanoes are everywhere. Magma's everywhere. So you can see the picture of Mount St. Helens, the actual ash flow. Not the ash that was caught up in the wind that was deposited all over the United States, essentially, but the actual predominant ash flow spans the entire state of Washington, right? That is the amount of power Mount St. Helens had to send its dominant pyroclastic debris across the state. Yellowstone's also a volcano. Yellowstone's actually a gigantic volcano. Look at that caldera in that top picture. It's huge, right? We have evidence of Yellowstone exploding in the past because we can find the ash beds, the result of the explosion of Yellowstone, throughout the continental U.S. Look at Mount St. Helens and how big and how disastrous that was. Mount St. Helens affected the weather in the year 1980 throughout the United States. It affected the Gulf Stream. It affected so much stuff. Look how big that ash flow is compared to the ash flow sizes of Yellowstone. People, you can watch sci-fi movie, made-for-TV movies about Yellowstone exploding and ending the world and stuff like that. That's a very real occurrence. If a volcano of sufficient size decided to erupt, it could cause untold devastation throughout the world, not just in its localized area, right? As I said, Mount St. Helens, that pyroclastic ash flow showing this little red blip up here in Washington, that ash technically made its way all the way across the continental United States. Imagine the destruction of the Huckleberry Ridge ash bed and what that could do to the area. Picture from Yellowstone. If you have a good chance to go out and visit Yellowstone, highly recommended. Very fun. This is, I believe, is the Mammoth Hot Springs. Kind of smells like eggs because there's sulfur involved, but definitely worth visiting this area. There's Mammoth Hot Springs. There you go. I've been here a couple times. Always worth the time. Unique, right? And you get to see geology in action in a way you don't get to see in many other parts of the world, right? The Mammoth Hot Springs are built up of the particulate of the hot springs, of the pressure being released and being erupted. Grand Prismatic Pool. Again, volcanic flows, volcanic eruptions, pressure being released, things of that nature, creating this iconic imagery. That picture of Yellowstone, again, going to show the size of what we're talking about here, right? Let's cross our fingers that Yellowstone stays dormant for quite a long time. And honestly, there's no reason to think it wouldn't. Sure, volcanoes do what they want to do when they want to do it, but volcanoes also are a mechanism to release pressure of magmas and lavas. So it's Volcanism is a very active subject. It's fun stuff. All right, let's go over a couple examples of volcanism and volcanoes in our everyday life. Columbia River basalts. When I say basalt, you should know from last chapter, basalt is an igneous rock. Basalt means magmas and lavas. So the Columbia River basalts, what we're looking at in this picture here, are the result of igneous flows and volcanic eruptions. The fluid basaltic lava extruded from crustal fractures that we call fissures. The magma essentially billowed up, similar to what's going on in Hawaii. Over time, erosion and weathering, we'll get to that, carved this river through the Columbia River basalts, the Palusi River, I believe, giving you this Grand Canyon-esque looking geology. Cool stuff, right? The interesting way that volcanoes work give you a lot of the iconic geology of the Western United States. All those rocks and all those Devil's Towers and what have you exist because, as shown here, you have the remnants of where volcanoes once sat. For example, Shiprock here in New Mexico, as shown that geologist sketch over there, is actually the conduit of an old volcano. Volcanic rock tends to be very hard, especially compared to sediment. So a volcano once stood here, it stopped erupting, and then over time, the volcano itself eroded away. That's what happened. Again, when we get to erosion in later chapters, we'll discuss that. As rock sits there, it gets hit by the rain, gets hit by the wind, etc., and the softest rock will move out. But the hard rock in the center of that conduit survives longer, giving you these shiprock standing, interesting looking geology. So as I said before, a bit with Yellowstone, well, volcanoes on one hand do what they want to do. It's not necessarily a random event. Volcanism is very much associated with plate tectonics. We talked about that in chapter 2, right? We have certain rocks appearing in certain locations given the chemistry and given the mineral makeup of the rocks. Basaltic rocks are commonly found in oceanic and continental settings. Granitic rocks are rarely found in the ocean, right? If you are someplace with a lot of basalt, there's a good chance that at some point that was underwater. And that's actually in the UP. We are mostly surrounded by basalt around here because when that igneous rock was extruded, we were underwater. The mid-continental rifting system, that goes into something off topic for this particular conversation, but it's kind of cool to know that granite is commonly found on continents and basalt is commonly found in the ocean. As I said before, volcanoes very much playing with plate tectonics. This picture shows you that the vast majority of volcanoes lie on or nearby active plate tectonic zones. Why do Mount St. Helens erupt? Well, because there's active tectonics going on there. We talked about that in a couple chapters ago, right? Why is Iceland so far back to volcanoes? Because of the Mid-Atlantic Ridge system. Yes, there are volcanoes not on active tectonic zones. Hawaii being a key example about that, correct? But there's also reasons in geology why those exist. The magma hotspots, for example. This is a complicated image. It's better shown in the book, I'd say, because you can get closer to it, describing all the different volcanic activities and why they produce what they produce. Different convergent and divergent zones, plate boundaries here, there, everywhere, describing the different volcanoes we see. Again, we can talk about the continental plate collision showing up in the Aleutian Islands, the volcanism up there. We can go to the Mid-Atlantic Ridge system. For your oceanic divergent plate boundaries, Oregon, Iceland, we can talk about that. You can have intraplate volcanism, such as Hawaii or in India. You can also have divergent zones, such as the Horn of Africa escaping. You get volcanism there, but you can always tie volcanism to some form of tectonic activity. Volcanoes don't appear where magma is not going to push through, right? Oh, I guess, do we go deep into both? Oh, we do go deep into all of them. Cool. Here's a zoom in on everything I was just explaining. Divergent plate boundaries causing the Iceland volcanoes. Diverging continental boundaries causing the rifting in Africa. This is an active rift zone. If you go to Africa, you can watch a continent being pulled apart right in front of your eyes. That's pretty cool, right? Subduction zones, we talked about, are very common. That's your Mount St. Helens, that's your Ring of Fire in the Pacific, things of that nature, as shown here and here. And yeah, this is kind of going over, this is rehashing of a third time for these examples, things that we already should have at least a decent understanding about. Subduction zone happens, the plate gets pulled underneath, gets hot, gets pressure, melts, the rock wants to move upwards because of pressure, eventually erupting again, forming new crust, forming new islands, etc., which then gets cycled through the rock cycle. It's called cycle for a reason. Intraplate volcanism, as discussed before, with Hawaii and Yellowstone is another example of that. The magma is going to go someplace eventually. When that magma goes someplace, usually some form of volcanism erupts, be it a nice slow volcanism that is Hawaii, or the big scary volcanism that could be Yellowstone. So short-term predictions. Volcanologists, what do they actually do? How do they predict when volcanoes happen? Well, volcanologists don't actually predict when volcanoes happen. Volcanologists rather read signs and signals that say something's happening within the volcano. Sort of a higher stakes version of the weather, right? If you look at a volcano, you see its size change, and you see its shape changing a little bit. That volcano used to be taller. I wonder why that is. Well, maybe some of the magma chamber found a place to go, drop some pressure, volcanoes falling in on itself, maybe it's about to collapse. Quakes would be an example of this. Earthquakes are essentially a release of pressure. If you have an increase in the amount of earthquakes, that's because you have an increase in pressure, right? Gas emissions, temperatures of hot springs, all these things spring into account because, again, a volcano is a release of pressure, and that pressure comes from hot, melted rock. So that is the end of this chapter. I would argue, again, volcanoes are not something that you're unaware of. Volcanoes are, when you think of volcano, you're probably thinking of it correctly. That being said, there's a lot of minutia, a lot of fun, interesting details about volcanoes that I think is worth knowing about. Volcanologists do a very important job in trying to ascertain the possible damages of volcanoes and preventing loss of human life and property. But at the end of the day, a volcano is kind of gonna do what it wants to do, because that's a lot of power. You can't really stop it. So I'll end recording for today, and then we can go on to questions if you want.